Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In the previous lectures, we were working under the assumption that you're familiar with the concept of making predictions and getting probabilities and multiplying vectors and matrices. So it was a little fast-paced in order for us to build on what we already know. In this lecture, I'm going to be a little more lenient and walk you through some numerical examples to solidify these ideas. Don't worry if you don't understand everything in this lecture right away. It might help to see some code first and then to return to this lecture later once you have some context for what we are trying to do. If you are already comfortable with the feedforward operation and doing calculations in matrix form, you can skip this lecture, otherwise keep watching. So let's set up the problem. Our training data, as you know, is a combination of inputs and targets. We call the inputs x and the targets y. In this specific case, we are going to have n equals 3 and d equals 2. That means in our experiment, we collected 3 samples of data, and there are 2 input features for each sample. First, we'll consider binary classification, and then we'll consider multi-class classification using Softmax. Our data is as follows. The 2 input features are has technical degree and hours of time spent per day studying deep learning. The binary output feature is whether or not the subject will succeed in deep learning. We can see that one of the input features, has technical degree, is binary, so it's either going to be 1 if true or 0 if false. We can see that hours of time spent per day studying deep learning has to be a positive real number. For example, you can spend 1.5 hours per day studying deep learning, but you can't spend -1 hours per day studying deep learning. So in this case, subject number 1 does not have a technical degree, but spends 3.5 hours per day studying deep learning. Subject number 1 succeeds. Subject number 2 does have a technical degree and spends 2 hours per day studying deep learning. Subject number 2 succeeds. Subject number 3 also has a technical degree, but only spends 0.5 hours per day studying deep learning. Subject number 3 does not succeed. And so this is our data set. One important thing to keep in mind. When we're doing prediction, we don't make use of the targets. The targets are only used during training. All we're doing during prediction is taking the input and calculating some output using the neural network. We hope that the predictions are close to the targets, and in the next section, we'll look at training, and the purpose of training is to make the predictions close to the targets. The structure of our neural network will be as follows. As you know, the input layer size is fixed to 2 because we have 2 input features. The output layer size is fixed to 1 because we have 1 binary output prediction. The output is going to predict the probability that the subject succeeds at deep learning. The hidden layer is of size 3. You might be wondering, how can we choose the right hidden layer size? This is in general an advanced and non-trivial concept, so you'll need to wait till later in the course for discussion on this topic. Let's for now just assume that a hidden layer of size 3 is fine. Let's now look at the weights in the neural network. Since every input node has to be connected to every hidden layer node, there should be 2 times 3, or 6 weights from the input to hidden layer. We can write them out all individually or as a matrix of size 2 by 3. One neat thing about the weight indices is that they tell you the nodes that they connect. So weight ij tells you that on the input side, it's coming from node I, and on the output side, it's going to node j. So weight ij connects node I from the previous layer to node j in the next layer. We can also have bias terms, and the bias terms are applied after the weight multiplication. Therefore, we need 3 bias terms. Let's call these b. Again, b can be represented as 3 separate scalars or as a vector of size 3. One thing to remember about these weights, I just chose them arbitrarily. They are completely random. Only in the next section, when we talk about training, will we be able to discuss how to appropriately set the weights to best solve our problem. Next, let's look at the hidden to output weights. Since every hidden node must be connected to every output node, and there are 3 hidden nodes and 1 output node, then we only need 3 weights in the hidden to output layer. Let's call this V. Again, we can represent each element separately or as a vector. And remember that we can also specify a bias term. Since the bias term applies after we multiply by V, the number of bias terms we need is only 1, since there is only 1 output node. In other words, it's a scalar. Let's call it C. Okay, so now that we have all the numbers we need, let's do some calculations. Let's take the first sample, so x is 0 and 3.5, and calculate the prediction p of y equals 1 given x. Initially, we're going to calculate this using summations. We are also going to use the tanh activation function. You might be wondering at this point, how do we choose which activation function to use? Like the number of hidden units, this is also an advanced concept, so we'll be discussing it later in the course. Notice how each of the terms in the summation corresponds to an edge in the neural network. Also notice how the 2 indices of W correspond to which input node and which output node it connects. So W11 connects X1 to Z1, W21 connects X2 to Z1, and we can do the same process to find Z2 and Z3. And here are the answers with actual numbers. So at this point we have all of Z for the hidden layer, 0.993, minus 0.74, and 0.604. What we would like to do next is calculate the output, p of y equals 1 given x. To do this, we need to multiply by V, add C, and take the sigmoid. Similar to the input to hidden weights, each of the V's also connects one node in the hidden layer to the output node. So V1 connects Z1 to the output node, V2 connects Z2 to the output node, and V3 connects Z3 to the output node. And so our prediction is, subject number 1 has a 70% chance of succeeding at deep learning. So that was a lot of work just to calculate one sample. As you may remember from my NumPy course and other prerequisites to this course, vectorized operations in NumPy are preferable. So we'd like to do vector operations rather than individual scalar multiplications, if possible. Notice how this is just equal to W transpose X plus B, using the vector and matrix forms. To prove to yourself that this works, let's plug in the numbers for W, X, and B. We see that we arrive at the expected answer. Now, of course, we can do the same thing for the hidden to output layer, so let's do that. If you plug in the numbers, you see that we arrive at the expected answer, 0.70. Now that we're on the theme of making things more efficient by vectorizing each operation, the next obvious question is, can we do this for multiple samples at the same time? Recall that we only looked at the first sample, but we have 3. So while we could calculate y1, y2, and y3 separately, this is clearly not what we want to do. Instead, we can combine these operations so that we can calculate y1, y2, and y3 all at the same time. Remember that the sigmoid and tanh functions apply element-wise, so the thing that you pass into tanh or sigmoid can be of any size. The weird thing about this is, W and X and V seem to have switched sides. So why do we have XW instead of W transpose X? The key to understanding why the weights get switched around is to remember how each sample is stored. When we're talking about a data matrix with multiple samples and multiple input features, it's an n by d matrix. So each row is one sample. But when we talk about that sample as an individual vector, it's a column, because vectors in linear algebra are by convention column vectors. So you have to remember that in the full data matrix, each sample goes horizontally, When a sample is by itself, it goes vertically. To further convince you why this works, let's consider a neural network of arbitrary size. The number of inputs is D, and the number of hidden units is M. Because every input must be connected to every output, W must be of size D by M. If we have n samples, then X must be of size n by D. And remember the golden rule of matrix multiplication: the inner dimensions must match. So the only way for this to be possible is if we multiply X times W. Now the inner dimensions are both D, which makes this valid. The output is of size n by M, which makes sense because we should have an m-size vector for every sample at the hidden layer. So hopefully everything so far has made sense to you. What we did was build things up from basic scalar multiplication, where we considered the value at each node one at a time, to vector operations, where we calculated an entire layer of nodes at the same time, to matrix operations, where we calculated an entire layer of nodes for every sample at the same time. As promised, we are going to move from Sigmoid to Softmax. When we go from Sigmoid to Softmax, it's helpful to look at what the targets will look like as well. Since when we use Softmax we have multiple output nodes, the output becomes a vector. Specifically, when we have k classes, we have k output nodes, and hence the output vector is of size k. This also means that when we're considering multiple inputs at the same time, where the input is a matrix of size n by d, then the output is also a matrix, but of size n by k. This is interesting because it suggests that if we use Softmax, then our outputs should be two-dimensional. But as you recall from our original dataset, the outputs are one-dimensional. So how can we reconcile this difference? The answer is that the targets in a neural network with Softmax output are more conveniently expressed as an indicator matrix. This is also equivalent to one-hot encoding, which you first saw in my linear regression course. Before we look at one-hot encoding, we should look at label representations. At a high level, labels have real-life meaning. For example, your dataset might consist of images of BMWs and Jaguars, and your classification task might be to differentiate between BMWs and Jaguars based on images of the cars. But as you know, when we're doing binary classification, we can encode these as 0 and 1. By the way, it should be clear that it doesn't matter which one is 1 and which one is 0. BMW can be 0 and Jaguar can be 1, or vice versa. It doesn't matter. This format is convenient because the output of a sigmoid is always between 0 and 1, and so our prediction becomes whatever the output is closest to. For example, 0.75 means we should predict 1. 0.49 means we should predict 0. But what happens when we have more than two labels? When we have more than two labels, the convention is to simply continue counting up from 0 and 1. So if we have 3 labels, the targets would be 0, 1, and 2. For example, if I have 3 labels, BMW, Jaguar, and Volkswagen, then in my code, I would refer to them as 0, 1, and 2. If I have 4 labels, the targets would be 0, 1, 2, and 3. The reason why we do this is different than the situation we have with binary classification. We are no longer rounding. So I'll never have an output like 2.7 and then round that to 3. That is not how Softmax works. Remember, Softmax outputs probabilities, so they'll always be between 0 and 1. The reason is because we'll be using these targets to index arrays. How exactly we are going to do that will be explained later in this lecture. For now, it's sufficient to remember that if we have an array of size k, call it A, then the first element can be accessed at A0, the second element can be accessed at A1, and so on, up to A of k minus 1. Let's now get back to one-hot encoding. If you don't remember what one-hot encoding looks like, let's recap with this example. Let's say I have a list of target categories, 051, 314, 20. It should be clear that there are 6 distinct categories here, since the numbers from 0 to 5 are present, and 8 samples, since the size of this array is 8. Remember that we name the categories 0 to k-1 by convention only. So 0 could represent BMW, 1 could represent Jaguar, 2 could represent Volkswagen, and so on. But clearly we can't use BMW, Jaguar, and Volkswagen to index a vector or matrix because they are strings. Therefore, we encode them using the numbers 0 to k-1. So if we have 6 different categories, then we'll have 6 different outputs in the neural network represented by the 6 columns you see here. If you have ever used the scikit-learn library, you may remember that it used to be the case that you'd have to encode your targets as integers from 0 to k-1. These days, the library also supports strings as targets, but internally, it's still converting those strings to integers from 0 to k-1. It's important to keep in mind that while we encode the targets using the numbers 0 to k-1, that doesn't mean these numbers have any meaning relative to each other. Let's say 0 means BMW, 1 means Jaguar, and 3 means Volkswagen. We know that 1 is closer to 0 than 3 is to 0. But does that indicate to us that Jaguar is more like BMW than Volkswagen is like BMW? Well, of course not, because we could have encoded these some other way as well. For example, we could have made 1 Volkswagen and 3 Jaguar. It's only a number that's representing the true category. But the numbers have no meaning relative to themselves. They are just distinct symbols. Okay, so back to one-hot encoding. We have these 8 samples and 6 classes. What does this mean? It means sample number 1 is labeled as category 0, sample number 2 is labeled as category 5, sample number 3 is labeled as category 1, and so on. We would like to one-hot encode these, and that means we need to put them in a matrix of size 8 by 6. What the original target tells us is where the 1 goes in the indicator matrix. So since the first row is category 0, that means the 0th element in the first row of the indicator matrix should be 1. Since the second row is category 5, that means the 5th element in the second row of the indicator matrix should be a 1. Remember, an indicator matrix only has 1s and 0s. Another way of writing this compactly is indicator of n minus k equals 1 if y of n equals k, otherwise 0. To help you solidify this idea, let's write some pseudocode to convert a 1D array of targets numbered 0 to k-1 into a one-hot encoded target indicator matrix. We'll be seeing this later in the code, so it's good to review now. As input, we take a 1D array, yin. It contains labels from 0 to k-1. We can then retrieve n, the number of samples, which is the length of yin. We can also find k since the max in yin is k-1. We then initialize a matrix of zeros of size n by k. Next, we loop through each target in yin, and we set the corresponding y out to 1. It should be clear now why the values in yin must be from 0 to k-1. It's because they are indexes into the y out indicator matrix in the second dimension, which is of size k. One question you might have is, why does turning the targets into an indicator matrix make sense? Well, remember that the output of a neural network is a list of probabilities, the probability that the input belongs to each class. Remember that probabilities are for telling us about things that are unknown. Well, what about things that are known? Well, in that case, the probability should be 1 or 0 because there's no uncertainty. For example, what's the probability that you are watching a video for a deep learning class? The probability is 1 because it's something that has already happened. So the probability that you are watching a video for a deep learning class is 1. The probability that you are not watching a video for a deep learning class is 0. And so for the target indicator matrix, which is actually a matrix of probabilities, the probability that the label is the true label given the data is 1, and the probability that the label is any other label is 0. This is because they are targets. They are already known. The output probabilities from a neural network, of course, will be numbers between 0 and 1, since they are predictions, not certainties. But the goal is that, after training, the probability of the true target is higher than the probabilities for any other label. So for example, the target indicator might be 00100, which means the target label is category 2. And after training, we'd want an output prediction, something like 0.1, 0.1, 0.5, 0.2, 0.1. So the maximum probability corresponds to the target label. That's what our goal will be during training. One way to solidify this idea further is to write out an output matrix and mark down what each of the probabilities means. As usual, each row represents what sample we are looking at. Each column tells us which category we are getting the probability for. This is why the output of a neural network, when it's processing multiple samples at the same time, will be an n by k matrix. So for example, this entry represents the probability that y1 belongs to category 0 given x1. This entry represents the probability that y2 belongs to category 1 given x2. Let's do a simple example to determine whether or not a set of predictions matches the targets. On the left, we have a matrix of probabilities which represent predictions. Notice how every row adds up to 1. On the right, we have the targets. Technically speaking, every row adds up to 1 here too because they are also probabilities. In the first row, 0.7 is the maximum number, and it corresponds to the location of the 1 in the target table, so this prediction is correct. In the second row, 0.4 is the max, and it's in the left column, but that corresponds to a 0 in the target table, so this prediction is incorrect. In the third row, 0.6 is the max, and it's in the right column, and this corresponds to the 1 in the target table, so this prediction is correct. In the fourth row, 0.5 is the max, and it corresponds to a 0 in the target table, so this prediction is incorrect. In total, we got 2 out of 4 correct. We call this a classification rate or classification accuracy, and it is equal in this case to 50%. Note that if we were to do this operation in code, it would actually involve the argmax rather than the max. Remember that the max tells us the biggest value in an array, but the argmax tells us the location of the biggest value. In NumPy, this could be done as follows. Axis equals 1 means we take the argmax over the columns rather than the entire matrix. One important thing to note is that the argmax is the inverse of turning an array of integers with the values 0 to k minus 1 into an indicator matrix. So one way to verify that your one-hot encoding is correct is you can one-hot encode your labels, then take the argmax, and the result should be the same as the original. Now that you've seen how to turn a list of targets into an indicator matrix, let's do this with our original dataset. Recall that we had 3 samples and 2 classes. That means our indicator matrix should be of size 3 by 2, and the elements are shown here. Since sample 1 has the label 1, there should be a 1 in the target indicator matrix at index 1. Since sample 2 has the label 1, there should be a 1 in the target indicator matrix at index 1. Since sample 3 has the label 0, there should be a 1 in the target indicator matrix at index 0. Okay, so since this is our target indicator matrix, remember that after we do training, which we'll cover in the next section, our output probabilities should be something close to this target. So what we would like to get is something that looks like this. One thing that we have to be mindful of is that the numbering here is a little strange. Because for some things we are counting with a 0 base count. For example, the classes are numbered 0, 1, 2, and so on. But then some things we are counting with a 1 base count. For example, we've called the components of x 1 and 2, and the components of z 1, 2, and 3. This is further complicated by the fact that some languages like MATLAB actually use a 1 base count, whereas most computer languages use a 0 base count. So why do we do this? Well, it stems from the fact that machine learning is sort of a combination of math and programming. If you pick up any math or statistics textbook, you'll notice that the counts by convention start at 1. If you see a summation, most likely you'll see I counting from 1 to n rather than 0 to n minus 1. But if you pick up any programming textbook, you'll notice that the counts start at 0. Since machine learning is a combination of these, you're going to see both. Typically, when we're looking at equations, we are starting our counts at 1. But if we're talking about implementation details, we're starting our counts at 0. And so that's why for labels, because they need to index arrays, they refer to implementation, and so we start the count at 0. The moral of the story is, you should use the numbering that corresponds to the programming language that you're writing in. Since we are writing in Python, counting starts at 0. And finally, we are going to get back to how to actually calculate the softmax output. Since we don't know how to do training yet, I've just picked some random weights. Let's also assume that the input to hidden layer is the same as before, so we have 3 units in the hidden layer. Remember that now we have 2 output nodes, so the hidden to output weight matrix of V has to be of size 3 by 2, and the bias C, which applies to every output node, is now a vector of size 2. Since we don't know what these weights are yet, I've defined them here on this slide. For this particular example, we are going to again use the first sample x equals 0 and 3.5. Since w and b are the same as before, this means that z is also the same, so we can start our calculation from that point. Remember that z is 0.993 minus 0.74 and 0.604. Let's again do this calculation the naive way, going node by node. Instead of expressing the entire output equation directly, we can do it in parts. The activation A for output node 1, which actually refers to class 0, is the top equation, and the activation A for output node 2, which actually refers to class 1, is the bottom equation. Remember that these A's are what we get right before going into the softmax. So let's calculate A1 and A2. This is the contribution from hidden node 1 to output node 1. This is the contribution from hidden node 2 to output node 1. This is the contribution from hidden node 3 to output node 1. This is the contribution from hidden node 1 to output node 2. This is the contribution from hidden node 2 to output node 2. And this is the contribution from hidden node 3 to output node 2. Now that we have A1 and A2, we can calculate the softmax and hence the output probabilities. Not surprisingly, we end up with the same output probabilities as before, because I chose V and C, such that this would be the case. And remember I taught you in the lecture Sigmoid versus Softmax, how to choose the output weights so that using the Softmax would be equivalent to using Sigmoid. So if you want to know how I did it, you may want to review that lecture and confirm that my new V and C follow the rule that I derived there. Same as before, we could have done that all in one step using a vectorized operation. So if you want to confirm to yourself that this is true, you may want to write this down on paper and do some of it by hand. And of course we can go further than this and calculate the output for all of the samples at the same time. But at this point it starts just looking like the equation we had before with the sigmoid. Now the softmax just replaces the sigmoid. Okay, so now you know how to calculate the output of a neural network as a batch matrix operation using both sigmoid and softmax outputs. Now there is one more nuance we have to talk about. Recall that if our input dimensionality is D and the number of hidden units is M, then W is a D by M matrix. And since the bias term B is applied after multiplying by W, it is a vector of size M. So if we are trying to calculate the output for a batch of N samples, the next will be of size N by D. Now what happens after we multiply X and W together? Well, first let's recall why this is a valid matrix multiplication. It's because the inner dimension, which is D, matches on both sides. The result of multiplying X and W together is an N by M matrix, but W is only a vector of size M. Recall that matrix addition is element-wise. That means when you add two matrices together, they have to be the same size. So doing XW plus B, which we showed earlier, doesn't actually work mathematically. We know that what should happen is the bias B should be applied to all n input samples. For that to happen, we need to flip B so that it's horizontal, and then repeat it n times. This would give us an n by m matrix, and then we'd have two n by m matrices that we could add together. Luckily, NumPy doesn't require you to do this explicitly. NumPy already knows that it should add the same B to every row of the result. So in the end, no additional work is required in NumPy beyond just writing x.w plus b.